as it were. I have been trying to now forget the algebra and try to emphasize the, let me get to the whiteboard. Yeah, I'm trying to emphasize what I call the more intuitive and in a sense numerical or quantitative understanding. You never become a good engineer if you are not able to guess how the numbers will look like, and that is has been missing. I do not know. I mean, it comes by practicing problems, but as you saw in your mid-semester marks, I mean, 90% of you have forgotten that millimoles is not the same thing as grams per liter, and you have multiplied Vmax into. So the question is, I mean, you've got by definition, then you're not able to solve the problem. Half of you have not realized that a PFR requires an integration across time, and the fact that S is varying. I mean, not half, 80, 70, 80% of you. So these are mistakes which are not mathematical mistakes. These are conceptual, fundamental mistakes, and it is important to sort of emphasize in the class without going into the algebra and the differential equations. We will do that. But if you don't have a feel for what is happening, then it is a very serious problem. And so, I mean, the point is rather simple. I mean, and I will illustrate it with a very simple mechanism, and this has all kinds of interesting permutations and combinations. See, any reaction of the form that enzyme kinetics is essentially at some concentration of substrate, it is zero order. Right? And this is first order. And this is first order, and the transition from zeroth order to first order, as it were, this transition is actually determined by the value of K. So the lower the Km, the later it transits from zero order to first order. And so, as you know, that whether it is PFR, CSTR business, or whatever it is, oh God, it started right away. Can you hear me?
Yes,
Hello?
sir, we can hear you.
Yes, sir, we can hear you. So the point that I'm trying to make is very simple and very obvious, but it's conceptual, that this transition from zeroth order to first order kinetics is determined by Km, and Km can change. Km can change because of inhibition. Km can change because of, as I will demonstrate, by mass transfer. Effectively, you will see Km changing, and I will demonstrate how. And then, of course, substrate also gets consumed in the reaction. And therefore, as I was saying in the last class, that a PFR performance is the fact that the substrate concentration across the length of the PFR is going to fall like this. And this is the outlet S. So this is S, and this is S in, and this is S out. And so really, as far as you are concerned, you have ds by dt, which is the same thing as V. V, as defined by definition, is ds by dt, right? For a closed system, is equal to some function of S. And therefore, because this is ds by dt, you can find out by integration that what is the amount of substrate that is consumed. And in a CSTR, the performance is this, S out. S out is the same as S. There is no such thing as length. So many of you have drawn a PFR like this. I mean, it's amazing. So in a CSTR, S out is the same as S throughout, because all the substrate concentration here is S out. That is the definition of a CSTR. This is S out. And S in is some number. S in is some number. Doesn't really matter. It's S out which determines everything. And so all the reaction, V is ds by dt. V is a function of S, but this is a constant, which is S out. So the reaction rate is a constant. It does not change across the length of the reactor. And obviously, therefore, a PFR's performance will be better. How much better? How much better will really depend on K. Because if it is zero order reaction, then this change in substrate concentration, if the substrate goes from here to here, then CSTR PFR performance will be exactly equal. So if your substrate in is very large or Km is very small, your CSTR and PFR performances will be exactly equal. And that approximation is allowed then. Suppose you know that the substrate in is, and I should put it in moles now. Suppose the substrate in is 1 molar and the substrate out is 0.1 molar or whatever, 90% conversion, and my Km values are 10 millimolar, which is actually 0.01 molar. If Km is this, then as far as the CSTR is concerned and a PFR is concerned, they are the same, and this kind of conversion can be solved by the CSTR equation. Because it really doesn't matter, because both give you Vmax. From 1 molar to 0.1 molar, this is 0.1 millimolar Km. So your V is equal to Vmax. So, which approximations to use when is very important to understand this. As I showed you in competitive inhibition. If you have very high substrate concentrations, you don't bother about competitive inhibition. So which approximations use when you can use an algebraic equation, when you have to actually integrate, really depends on a very good understanding of the numbers that you are working with, the numbers that you're crunching. And that is why I wanted to solve this problem. So when I ask you the more complex question, what is the performance efficiency of a PFR by a CSTR, and how does this performance efficiency change with respect to changing values of, say, Km, then it seems like a very difficult question. It is not, as long as you understand this very simple concept. And these are, so you have to think about what is being taught to you and think about the algebra. Right? So, let us sort of move ahead, and these are the kind of things that, I've not been mentioning because I thought these are things that these concepts have been clarified in reaction kinetics. So let us think of the fact that the bead has, so we have external mass transfer, that is what I was doing in the last class, and we have external mass transfer. And I think we will sit and solve problems because I think that is the only way to do it. We have external mass transfer, even though it's simple algebra, you have to solve these problems. And transfer, sorry, this is getting cut. And this mass transfer essentially means that there is a zone of diffusion around it. And this here is S0, and this here is S. And this is the S that the enzyme sees. It sees a lower S. But this is what you measure. So please keep this very simple point in mind. This is what the enzyme sees, and this is what you measure. So you say this is a substrate concentration by which the enzyme is giving a reaction. So you say V is equal to V some, let us say Vm, and you're doing an experiment. You will say V max S0 is Km plus S. Right? So this is your plot for different substrate concentrations S. S0. But this plot is actually of S0 versus V, because there is no way you can plot S. But the real reaction is taking place at S. So think of the fact that S is now much lower than S0. So essentially, think of this scale. And that's why I'm deliberately, I will do the algebra later. Think of this scale, and this scale is now shifted. So your plot is like this. Are you getting this point? I am just x-axis, I'm expanding. Let us say I expand the x-axis. Suppose I say take this data and I expand it by double. This plot, suppose this is 1. And now, this never happens, but suppose it is 2. Suppose this is 2 now. So 1 should show up as 2. So it will reach maximum at 2, not at 1. And so this scale is expanded. So for all practical purposes, what has happened? Km has changed. Are you following this argument? Hello? If I just argue without the algebra, is it comfortable enough? Because without the algebra tends to simplify as well as confuse. Are you getting the argument that actually you are saying that V is equal to V max? Oh. Sorry. You are saying that V is equal to half of V max. V is equal to V max by 2 when the substrate concentration in your experiment is 1 gram. So your Km is therefore 1 gram per liter. Right? But actually the S here is actually 0.5 grams. So this is the real graph. This is the real graph. There is no such thing as real. This is real graph This is the real graph of V versus S as far as the enzyme is actually concerned. If there was no external mass transfer, the real graph. But because of external mass transfer, this point has now shifted here. Because this substrate concentration S0 translates to this substrate concentration here. So I actually have to expand the scale. So when I expand the scale, I will notice that it will reach Vmax at any time. It will reach Vmax, or let us say close to Vmax, or 90% of Vmax at say 5 grams. But now it will reach it at 10 grams. So the scale has been doubled. So for all practical purposes, the only thing that has changed is Km. And so there is a Km apparent exactly the way there was complete inhibition, even in the situation of external mass transfer. So you see the similarities between the two methods. Yes? So right. I mean, if you don't say anything or be silent, then it's very difficult. I can't see your faces. I am not taking, that is why I prefer a offline class. Is this clear? Somebody has to say something.
Yes, sir.
Yes. Yeah. So now we were talking about let us do the equations now. The simple enough equations, and let us keep it simple. So we were saying that the external mass transfer, I should not have rubbed this out. So this is Ke, which is, remember, delta dA by delta, right, for the film transfer coefficient. Ke Se minus S, S naught minus S is equal to Vmax S upon Km plus S. Right, the mass transfer is equal to this for the surface, and as I said, I defined three things. I defined a dimensionless X, which was nothing but S by S naught. Notice that S by S naught, this is S, this is S naught. So S by S naught is 1 when there is no mass transfer, and it's very, very small when it's mass transfer. So the value of X essentially determines the mass transfer, is a measure of the mass transfer. The value of X equal to 1 means no external mass transfer, which means diffusion or Ke is very, very high. If this is very large, then obviously the driving force, the voltage difference, as it were, in Ohm's law, S naught minus S is very small. So S by S naught is close 10 into 1, right? And we define also the Damp-Kohler number, which is obviously, rate of reaction divided by rate of diffusion is a proportion. So in this case, the maximum rate of reaction divided by the maximum rate of divided by the maximum rate of mass transfer. So Damp-Kohler number, again, you can see that when Damp-Kohler number tends to 0, as it tends to 0, this means Ke is very large. You will notice that X will tend to 1. Right? And I also defined something called kappa very simply, which was come on, let us have some answers. What was kappa defined as? Based simply by the Km by S naught. Again, I told you the role of that Km plays. The role of that Km plays is essentially ensuring whether there will be an impact at what substrate. You might have a huge amount of mass transfer resistance, but if your S naught is really, really large compared to Km, then you will not see the effect of mass transfer. As I told you, right? Because S naught is large, Km is small, you have zeroth order reaction. Whether it is S naught or S really doesn't matter, because your velocities will be close to Vmax anyway. So you will not see external mass transfer as long as Km is very small compared to S naught. Because S will also be much higher than Km, and so both S naught and S will give the same velocity, which is close to Vmax, because of the advantage of zeroth order reaction. So the concepts involved are circular. We use the same concepts, but we do a different kind of algebra. Is this argument clear? So kappa values also then impact. So very low values of kappa will not impact on external mass transfer. Right. So what do we have here? What is the basic expression for Damp-Kohler number? Ke. Come on, let us have it. S naught minus S. Or let us take, this is the basic equation. So we write it in terms of Damp-Kohler number. So let us write it like this. Let us write it as Ke S naught. No, sorry. Ke S naught 1 minus S by S naught. Okay, and let us bring the Vm this side. Right, is equal to S upon Km plus S. and then this becomes your 1 by Damkohler number. So this becomes 1 by dA. Okay, and this becomes 1 minus, this becomes 1 minus x. Okay, and what does this become? S upon Km plus S. Divide by S naught, what do you get? A divide this by S naught, numerator and denominator. So S, this by S naught, this by S naught, this by S naught. So what do you get? This is S by S naught, again x, right? All of you following this? What is Km by S naught? Kappa plus x. So this is your expression in dimensionless terms. Okay? 1 minus x upon dA is equal to x upon kappa plus x. Now, this very simple reaction model can be used to predict this is the relationship between x, kappa and dA, which I just now pointed out, that as x tends to 1, dA tends to 0. As dA tends to 0, x tends to 1. But also as kappa tends to 0, the reaction rates go up. So you can see the relationship, and I want you to plot this. Go back and study this expression. It's a very simple algebraic expression. See how these plots look like for different values of dA. So how does, what happens when dA changes? How is x impacted? Okay, and for different values of kappa. Okay, the other very logical and more logical actually, as a matter of fact. So this is derived from this, but the other expression that I will derive, I should hold this expression here, is the thing that you are really interested in, which is the efficiency of the reaction. And what is the efficiency of the reaction? We define efficiency of reaction, or whatever efficiency R, is equal to the observed reaction rate divided by the reaction rate when there was no diffusion, right? I talked about this. Reaction rate when there is no diffusion. When there is no diffusion. When there is no diffusion control. So remember, as I pointed out from these expressions, that this will be one under two situations. When Damkohler number is close to 0, because Damkohler number, remember, was your Vmax upon KES naught. So if KE is very large, by definition, so when Damkohler number tends to 0, your efficiency will tend to 1. Also, when kappa, when S naught is much larger than K, then also this efficiency will be equal to 1. So now you see the relation. Now let us see whether you can derive the relationship between the efficiency of the reaction and using this relationship, its relationship with Damkohler number. For low values of Damkohler number, for high values of Damkohler number. Okay. So what do we get? So what is efficiency factor? Can you derive the expression? So observed rate of reaction. What is the observed rate of reaction? So observe, I'll write it here so that we can solve it here. Let us do it here. Vm observed rate of reaction is Vm S upon Km plus S, right? And the reaction rate with no diffusion would be Vm S naught upon Km plus S naught, right? That is what we talked just now. So can you sort of see what it happens? S naught by S naught, S by S naught. So now tell me, okay, why should I sort of solve this out? Tell me, what is it in terms of X and K kappa? Some of you please do it. It is a rather simple algebra. So hello, are you there?
Yes, sir. Yes.
हाँ, तो जरा करिए भाई रत्नेश जी.
Yes, sir.
हाँ, तो S by S, ये basically S into Km plus S naught upon S naught into Km plus S. यही है ना. और ये आपका X हो गया anyway, ये X हो गया, this is X anyway, और इस सबको S naught से डिवाइड कर दीजिए. तो X बताइए, ये S naught से डिवाइड कर दीजिए, तो ये कापा
प्लस
और नीचे वाला होगा इसको S नॉट से डिवाइड करिए तो ये क्या होगा?
So kappa plus X.
So your efficiency therefore becomes, because if you derive these things, then you are much more comfortable. Kappa plus 1 upon kappa plus X, right? Now tell me, what happens when kappa increases? What happens when kappa decreases? What happens when X increases? And what happens when X decreases? How will the plots look like? What happens when kappa goes to 0? Does that make sense to you? What happens when kappa goes to 0? What does the efficiency happen when kappa goes to 0? This is equal to, suppose kappa is 0.
So 1.
So you see, as kappa goes to 0, this goes to 1. This is the argument about the fact that Km is very small. So this is Km is very small, so it is not impacted. So you have this circle here and the film, but as the substrate concentration is high, this concentration is low, but the enzyme is so damn efficient that whether it is S0 or S, it is always 0th order reaction. It is always 0th order reaction, and hence, for all practical purposes, if kappa goes to 0 and it is a 0th order reaction, whether it is S0 or S, my efficiency, it is as if external mass transfer doesn't exist. It actually does exist, but it is not going to impact on efficiency. Now let us look at the other thing. As X changes, what happens when X becomes close to 1? As X tends to 1.
Then also it will be 1.
Then again, the efficiency is 1. Sorry. Notice that as X goes to 1, so as kappa tends to 0, it tends to 1. As X tends to 1, again this is 1. But this is 1 for a different reason. As X, now it doesn't matter on kappa. This tends to, because now S0 and S are quite close to each other. So there are two ways in which you can increase efficiency equal to 1. You can bring it about by having a very, very high affinity enzyme which runs at Vmax independent of the substrate concentration that it sees. The S that it sees doesn't really matter what it sees, because it is such an efficient converter, such high affinity, not an efficient converter, it's such high affinity that even at low S values, the V is approximately close to Vmax. Because remember, this is S upon Km plus S. And so S upon Km plus S is 1, whatever the hell happens to S. So this is one way to make it 1. And the other way to make it 1 is actually to ensure that S0 and S are very small, because this is very high. Okay? Is this all right? So now let us sort of, so is this argument clear? Now I'll have to rub this out, unfortunately, and then I will forget what I calculated. So please, you people should also, as I told this long time ago, use a paper and pen and write down what I'm writing, because that way it gets internalized. Otherwise, you have to look it up all the time, what lecture notes, and that is why you cannot solve answer sheets unless you have 3 hours of time. This has to get internalized, and the only way to get internalized is when you actually do this. Okay? So now, what happens when dA is large? Or let us say, when S is very small. Let us say what happens when the other thing, when S is small, because you know your is small, because you know you have diffusion limitation. So D is actually small as D. Sorry, D. What is dA? I've forgotten. dA is Vmax upon Km. Vmax upon Km. V upon Ke. S0. Vm. So now notice that when dA is large, sorry, when dA is small, it is actually large में ये होगा ना, sorry, उल्टा बोल रहा हूँ, sorry, I'm so sorry. It's all right. So when dA is tending to 0, then you have no mass transfer. but dA is tending to large values, then you have a problem because Vmax is high, this is small. Okay, so dA is large. As dA becomes large, you have trouble because dA is large means you have mass transfer, external mass transfer present. So when dA is large, their V is equal to Ke S naught minus S. And so I am going to say that this is equal to Ke S naught. Because S naught is very large, because this differential will increase. The drop, as they say, the pressure drop, because this will become, see, because if diffusivity is small, if the rate of diffusion is low, slow diffusion, then obviously to match the reaction rate, S naught minus S has to increase, right? This is a standard Ohm's law kind of logic which we use for all mass transfer and diffusive processes, right? So now tell me what will happen to the can you sort of, we derived the efficiency with this was the expression that we got, right? Arey, kya ho raha hai ye? Okay, you look at it. I will have to switch it off. You derive this in terms of dA. Now you have the expression for dA. You have the expression for this in kappa and this. Now tell me when dA is large, what is the relationship between efficiency and dA? I'll have to put this on. These kind of things are important. So we have this expression here for dA, and we have the expression here for efficiency. And I am now saying that we solved it for situations where efficiency was 1 and dA was tending to 0. Now let us take the condition when dA is large and tell me what is this as a function of dA. So I know, I've just written down here, right? That dA is equal to Vmax Ke S naught. And I've also said velocity here when dA is large can be approximated by V is equal to, sorry, this keeps giving problems. I'm also saying that V is approximately Ke S naught minus S mein hata diya when dA is large. So V is approximately Ke S naught. So what is efficiency? Come on, I thought it would be obvious. So when dA is large, we have this expression for you. We have these basic expressions for you, right? And I want to find out what is efficiency, given the fact that efficiency is the same thing as observed rate of reaction. Now the observed rate of reaction is this thing, Ke S naught, right? So भैया ये आप लोग अब तो करिए भाई, है ना, divided by Vmax. This is, I think I have to get rid of this laptop. Vmax S naught upon Km plus S. And this is what? This is 1 by dA. I hope you realize this. Right. So tell me, efficiency is 1 by dA और ये ऊपर आ जाएगा Km plus S naught upon S naught. ठीक है ना? ठीक है?
Yes, sir. That is kappa plus 1.
This is kappa plus 1. So efficiency when, sorry. So the third expression that we can derive for large dA values is efficiency is equal to क्या बोला आपने? Kappa plus?
So kappa plus 1 by dA.
Kappa plus 1 by dA, na?
Yes, sir.
You have rather simple expression for large dA. dA large. So you can see what I was trying to prove very simply, that it is an inverse function. And it is a 1 upon x kind of function when kappa is small. When kappa becomes large, then it becomes 2 upon x, 3 upon x, 4 upon x, and so on and so forth. ठीक है ना? So, my problem is that we can keep on doing this algebra indefinitely. It is not a very big deal. Okay, so what I want to do is solve some few problems, please. I mean, I'm getting very worried. Let us solve some problems. Let us sort of put up some imaginary numbers or something, and let us do them, right? So let me sort of rub it and give you the problems. What is the time? 9:52 or 32? 32. What time? Okay, or shall I go ahead and you can solve them on your, let me give it and then I will start with with internal mass transfer. Now let us sort of take something, मेरे पास कहीं कोई problem solve पड़ा हुआ है. So Vmax, okay, let us take simple values. Vmax is equal to 1 millimoles per minute. Please remember this. Okay, units. Okay, and I say Km. The known Km is 20 millimoles. The apparent Km that I find out from lab experiments is 40 millimoles. This is what I measured in my lab when I have mass transfer. Right? And I want you to find out what is the dA values and efficiency when S is equal to Km, when S is equal to 20 and when S is equal to 40. चलिए करिए इसको. Question number 1, S is equal to 20. Question number 2, S is equal to 40. Find out the value of dA. Does it get impacted by changing? So when I do the experiment, sorry, S naught. I have done a lab experiment and you have been told that under the conditions of working, Km apparent is 20 and Km apparent 40. Km apparent is 40 and the real Km value without external mass transfer is 20. Vmax is 1. I told you just now expansion, and I want you to find out the dA values and the enthalpy these values when case 1, when S naught is equal to 20 millimolar in my reactor, and second when S naught is equal to 40 millimolar. बताइए. पहले एंथैल्पी एफिशिएंसी निकालते हैं. चलिए क्या होगा एफिशिएंसी? Observed rate करिए भाई. Observed rate upon rate without diffusion. Let us use first principles. Let us not follow formulas. What is the observed rate at S naught is equal to 20?
So Vm S naught by Km apparent plus S naught.
Vm S naught, observed rate will be S upon Km plus. S naught upon Km plus S naught. But now this will be Km apparent.
Apparent.
Got the point? So it will be S naught, but now it will be Km apparent. And this will be Vm S naught upon Km true plus S naught. So notice I wrote the same thing in different ways. Earlier I was writing it as Vm S upon Km plus S, and this was Km true plus S upon Vmax S naught upon Km plus S naught. And now I've written it as S naught, but I've changed the Km. Both have the same impact, but only for a particular condition. These do not translate algebraically to equivalent statements. They will become equal for a specific case. S naught is equal to 20 or S naught is equal to 40, and they will be different in each case. And I will ask you to find that out also. So tell me what happens when S naught is equal to 20. What is the efficiency?
So 2 by 3.
It is obviously 20 ये हाफ हो जाएगा, नीचे वाला रिएक्शन रेट हाफ हो जाएगा और ऊपर वाला रिएक्शन रेट क्या होगा? It will be half Vmax, right? Or because the true rate is half Vmax और ऊपर वाला क्या? 1/3 Vmax.
1/3.
ठीक किया? 20 by 40 plus 20. You are right. Absolutely right. So what is the efficiency? 2 by 3, na?
2 by 3.
Achha. So the efficiency in this case is efficiency is equal to क्या हुआ? Oh. Next वाले में क्या होगा?
So 3 by.
So efficiency is 2 by 3, and here the efficiency is 3 by 4. Right?
Yes, sir.
So notice that as S0 is increasing, the efficiency is tending to closer to 1. Because now for the same value of actual Km, 20 millimolar, and if I had made S0 like 100 or something, then the kappa values change, because Km by the real kappa values, remember, are kappa is K S0, sorry, Km by S0. If S0 keeps increasing, kappa tends to reduce. And as I pointed out, that as we increase S0, my efficiencies will improve and slowly tend to 1. It is at low substrate concentrations that a further lowering, it is like a poor man and a rich man, you understand? A rich man who takes a 10% hit, he does not starve. But a poor man takes a 10% hit, he starts starving. So when S0 is large, your efficiency is going to be impacted much less. And when S0 is small, your efficiency is going to be impacted much more. Okay, now what about the Damkohler number in both cases? You people have to solve it, because you know this is the only time you solve. You don't go back home and solve. Hello. पहले अच्छा, Damkohler नंबर निकालने से पहले x निकालिए और फॉर्मूला से चलिए आप लोग, जैसा आप लोग चाहते हैं. मुझे पहले x बताइए क्या होगा. So I will write 2 by 3 is equal to x, बताइए, 1 plus 1. I am solving this problem. 1 plus x. Is this okay? Hello? What is the formula that I wrote? That is why I said you should copy it out. The moment I rub the board, it is gone. Remember that original derivation that we did for efficiency?
Yes, sir. X into kappa.
X, kappa plus 1, kappa plus x. Right?
Yes.
भाई आप लोग क्या कर रहे हैं? ठीक है ना? तो kappa 1 है, भाई KM2 देखना पड़ेगा ना. ये तो हमने आपको जबरदस्ती प्रॉब्लम को मॉडिफाई करने के लिए ऐसे बना दिया. इन KM apparent, तो ये हुआ, तो ये हो गया. तो व्हाट इज x?
So we have to like consider KM apparent, right? Not.
No. KM apparent is an experimental finding which is a distortion of the correct method. You see, it is not a good method, but I mean, biologists tend to use it. This is not a. What do you mean KM apparent? It's actually the fact that there is no change in KM apparent. This is an imaginary construct. The real thing that has changed is that actually instead of S0, you should have been using S. This is the correct way to work. So what I did here was a deliberate distortion, a game playing as it were. That, you know, who the hell as a biologist, as an experimenter, I am going to measure S. I am going to tell you that for different values of S0, when I plotted Vmax, I got a Km apparent of 40. But I know that Km real is 20. This is an artifact of an experiment, because what does it really mean? And I thought this is very obvious. It really means that when my reaction rate is half, my S, when V is equal to half of V max, which is 0.5, and I hope it is very obvious, then S, I thought you would use this rather than this logic. I deliberately sort of started saying, doing this. Then S that I have used is 40 millimolar. The S naught. I've used, that is why I'm calling it, so at S naught equal to 40, I got V is equal to half V max. But if there was no mass transfer, the S that the cell has seen is actually 20. Because if there's no mass transfer, the S that the cell would see is 20 millimolar. Are you getting this point? So when S naught is 40, I have V is equal to V max, but actually the cell sees 20 millimolar and its Km is 20 millimolar, so V is equal to half of V max. So V at V is equal to half V max, at V is equal to half V max, the experimental condition by S naught is 40 millimolar and the substrate concentration of the cell is 20 millimolar. Therefore, the Km true is actually 20 millimolar and the Km apparent is 40 millimolar. So therefore, really we should not be working with this. We should be working with this. Are you following this? Hello?
So could you explain again?
Think about it. Think about it. What did you do as an experiment? What did you do? You chose a substrate concentration of 40 millimolar and found that the rate was 0.5 millimoles. Notice Vmax does not change per minute. So you said V is half of Vmax, and what is the substrate concentration I used? 40. Therefore, my Km apparent, the Km that I observe, is 40 millimolar. Another person did the same experiment, but there was no mass transfer by some mechanism. Say the enzyme was not immobilized or something. And he found that when S was equal to 20 millimolar, he got a V is equal to V. Arey bhai, ye kya hai? This is very irritating. Now keep rubbing this, then this suddenly comes out. So, you know, so there are two experiments involved here. One is that at S, this is with mass transfer, you got V is equal to half of V max, which is 0.5 millimolar, and the substrate concentration that you used in the experiment was 40 millimolar. Therefore, you made the claim that V is equal to V max, S is equal to 40, and you made the claim that in this experiment, I observe a Km apparent of 40 millimolar. This is an experimental artifact of increased Km, that is why I call it apparent, because there is mass transfer. If there was no mass transfer, you would have got V is equal to half Vm at S is equal to 20 millimolar only. That is why Km true is 20 millimolar. Which also means that because of mass transfer, this is the enzyme and this is the film. S naught here and this is S here. S naught is this number and S is this number. Correct? Are you following this now? So X
Yes, sir.
is equal to half. Right? And please solve this expression and see whether you get X is equal to half or not. To do it algebraically, because from very early age, BTech students are trained to trust the algebra and not their intuition. I did it intuitively. The fact that 20 millimolar without mass transfer observed kiya, 40 millimolar observed kiya, but you use this formula and find out what is X. मैंने x हाफ प्रेडिक्ट कर दिया, सब्स्टिट्यूट कर लीजिए हाफ मैच करता है कि नहीं. You don't have to solve it.
Sir, we are
आ रहा है ना?
equal to
Sorry, I can't hear you.
I was saying that we are getting x equal to 0.5.
Sorry, you're getting 0.5, right?
Yes, sir, 1 by 2.
Yeah, because if I put this as half, then this is half into 2, which is 1, and this is 1 plus half, which is 1.5. 1.5, 1 upon 1.5 is the same as 2 by 3, right? Double it is 2 by 3. So x is equal to half. So I can prove x is equal to half by this method or by this method. So notice that when we are using a substrate concentration of 40 millimolar in the outside, I am going to get an S value of now. Suppose I use lesser concentrations, 20 millimolar, or suppose I use 80 millimolar. I want to go back, you to go back home and find out how enthalpy efficiencies change and how the driving force changes. So when outside is 40, it is inside is 20. Right? But suppose outside is 20, what will it be inside? And suppose outside is 80, what will it be inside? And how does it match the damp polar number? How does it change? The x not the x values, how does it change? And the enthalpy, not enthalpy efficiency, the efficiencies of reaction rate, how do they change as substrate concentration is increased or reduced? I want you to go back and solve these problems. Let us solve one part at least. So what is the damp polar number? So if I found out efficiency as what was it, 2 by 3, we found out x is equal to half. What is the damp polar number? एक तो मैं काम कर नहीं पाता हूँ, पेन हर बार गड़बड़ करता रहता है. What is the damp polar number? What was the expression for damp polar number? You use first principles if you can't do it, but we had a simplified version which I wrote just now. In terms of x, you forgot? This is the problem. That's why I said start writing. Otherwise, you will never remember.
dA is equal to 1 minus x upon x into kappa plus x.
Yes, dA. So 1 minus x. Actually, we wrote it as 1. Oh, sorry. 1 minus x upon dA was equal to x upon kappa plus x. You are right. तो बताइए dA क्या होगा? X half है. X is equal to half. So what is dA? And kappa is? What is kappa? Kappa, I hope you realize kappa is 1, right? Kappa is 1 because kappa is km, the real km. This you should forget, huh? Km and S naught is 20. So kappa is 20. So kappa is 1 and kx is half. What is dA value?
2 by 2. 3 by 2, sir.
3 by 2 or 1.5. Right? So you see, and I want you to calculate how dA changes when we use S naught is equal to 40. And I want you to ask you the question, will it increase or will it decrease? These are the questions that you need to. So even though this is very simple algebra, in mass transfer, internal mass transfer, we will have slightly more complex algebra, rather a bit of differential equations, but that's not very important. And then we will ask more complex questions, that what happens when both are present and all that. So before we get into complicated algebra or differential equations, I want you to have a feel of what is happening. So I want to ask you, how does dA whether it increase or decrease as I increase S naught? Enthalpy, sorry, again and again I keep on talking. Efficiency obviously will increase when I increase the substrate concentration because of that same logic that I mentioned right in the beginning of class. Zero order versus first order. The more the reaction is shifted towards zeroth order, efficiencies are 1 because they are not impacted by substrate concentrations. And as you increase substrate concentrations or you reduce Km, your efficiencies will tend to 1, independent of what is the actual mass transfer effect. So either your efficiency will be 1 either when mass transfer is not or not is negligible because your dE values are very high. If this is very high and mass transfer is negligible, then there's no problem. But if mass transfer is significant, then it really depends on the value of S naught. As you keep increasing, it becomes tends to 1. So as I reduce it, so now damp Kohler number is the mass transfer is Vm reaction upon K S naught. So by definition, you can see without thinking too much that if Vm is fixed, Ke is fixed. As we increase S naught, dA has to obviously reduce. Right? So you can catch your nose any way you want to. But catching it in different ways allows you to locate your nose very properly in your face. So that is the whole argument. So I could have used this much simpler question, but I deliberately twisted it around to get into this and then solve it again for X. So what happens to X? What happens to efficiency? What happens to dA? What happens to kappa as you increase substrate concentrations or you change Ke? These are the kind of few simple algebraic manipulations. If you go back and do, you will get a much better feel of the numbers and what is happening. The understanding will become much clearer. That is all I'm trying to suggest. Let us stop here. We have done very little in this class, but I think it's important that I could just write these equations and substitute numbers. That is not serving its purpose because you are not getting a feel of the subject. And next class, we will do the internal mass transfer. Thank you. Any questions? Okay. Thank you very much. Hello. Could you hear the last part of the conversation or was it gone?
Yes, sir, we can hear.
Could you hear earlier?
Yes, sir.
Okay, ठीक है. So any questions in the class? Okay, let us stop here and we will see in the next class. Thank you.
Thank you, sir.